All right, so let's do the example for the efficiency of a nozzle. So example. Consider here that you have a nozzle that I plot under this form. So this should be your control volume. All right, so on the control volume, on this case, we're gonna assume that there is no heat transfer and no change in potential energy. So we know the substance is steam. So let's say the inlet 1, and let's call for 2 the outlet. So we know the inlet is steam. We know the initial pressure is 140 psi, so LB in square. The initial temperature is 600 degrees Fahrenheit. And then the initial velocity is 100 feet per second. Now we know that at the exit of the nozzle, the pressure should be, the pressure is 40 LB in square, and that the temperature is 350 degrees Fahrenheit. And the question is to find the nozzle efficiency. So we need to find the efficiency of the nozzle. Okay, so if we go back to the notes that we did last time, again, if we do the HS figure, you don't have to redo this one, but I think it's good for the understanding. Okay, so maybe here, let's do something before we maybe start doing the figure, is that we know at the beginning is steam. So what does that mean? It's gonna be in this area, no? Okay, let's see what it would mean 40 and 350. So, that's the lecture note from the other time. So we need to go to the tables. So in English units, SI English units for steam. Let's see what would that be. So page down. This is steam. So let's see what would be what is the temperature? 350. See, we have 350 here. So 350, the temperature, the pressure is 134. So let me go to the other table. I can upload this. So pressure of 40. The temperature is 267, no? So what is the state? State 2 is also steam or vapor, no? Okay. So then can come to this figure over here. So we know P1, we know P2. So we know, for example, P1 is going to be much higher. Let's say P1 should be here. And let's say P2 could be here. We know that if we go through an isentropic process, you go on a straight line where you will have S1 equal to S to S. This would be the state to S. But in real life, what happened? You know that nothing is perfect and we're going to lose energy, no? You're not going to use perfectly the energy. So if you don't use perfectly your energy, what's going to happen to the entropy? It's going to increase, no? Because of the concept of increasing entropy of the universe. So that means we're going to end up somewhere over here. Okay, and on the figure, I don't want to add too much, but we say that this change over here in height should be proportional to V2 squared over 2, and that this one over here should be proportional to V2S squared over 2, okay? So it was defined that the efficiency of the nozzle was equal to the kinetic energy, the actual, divided by the kinetic energy isentropic, which is the ideal case. So that means we had V2 squared over 2 divided by V2S squared over 2. Or sometimes you can rewrite this as V2 squared divided by V2S squared. Okay, so what does that mean? Is that in order to find the efficiency, we need to find what would be the ideal or what would be the maximum velocity you can get at 2 if the system was isentropic, meaning that it was ideal. And now, what is the actual velocity at the exit, no? With the losses. All right? So that's what we need to do. So, again, I tell you, we add new stuff like isentropic efficiency, but the process should remain the same. So we have the control volume. What type of system is this? This is a control volume or an open system. So we can say applying first principle thermodynamics to control volume. What are you going to have? Q dot minus power plus M dot H1. But now be careful, we're also going to have kinetic energy because we have the V plus M 1/2 M dot V 1 squared will be equal to what? M dot H2 plus 1/2 M dot V2. So here could be V2 or V2S, okay? But let's just say in this case, I'm going to put V2 and let's first do V2. V2 squared, yes. I was so worried about stuff, I forgot the square. So now what do we know about this problem? You look at the figure. Is it any heat transfer? No. Does this system requires power or does it provide power? No. So this is 0. Then, because I didn't put it, but this is a steady state. So that means the amount of mass going in will be equal to the amount of mass going out. All right? So in that case, you can see that we could cancel all the ends. So that what do we have? We are left over with H1 plus V1 squared over 2 equal to H2 plus V2 squared over 2. And what do we need to solve for over here? V2 squared, we could just solve V2 squared over 2. So from here, we could say that V2 squared over 2, that we can substitute in this value, or you can solve for V2 squared, will be equal to what? Will be equal to H1 minus H2 plus V1 squared over 2. Okay, so in that equation, we know V1 is 100 feet per second. Can we find H1 and H2? We need to know two things, no? I state, do we know two things over here? Yes. Do we know two things over here? Yes. So basically, we go to the tables to find H1 and H2. So that's over here. H1, H2. We go to the table. So let's first find H1. So what do we know about H1? We know two things. P1 equal to 140. T1 equal to 600. And we actually know even more. We know the state is steam. So that means we're going to have to go to table A for E. So this should be A3E. A3E, I guess next one is A4E at 140. So hopefully they have that value, 120, 140. Then at 600 over here, H I think should be the third column, let's see. Should be that column over here. So at 140 and 600, we get 1,326.4. So H1 equal 100, 300, so 1,326.4, and this should be BTUs per pound. And then for H2, what do we know for H2? P2 equal to 40, and T2 is equal to 350. Again, table A4E. We find that, so basically what I was writing is, where's the camera here now? So basically I wrote this, for H2 would be 4350. So 40, let's go up. This one appear again. I don't know how to get rid of it. Oh. 40 is here, 350 is here, we're lucky. Is 1,211.8. BTUs LB. Okay, so now we can go and substitute into that equation. So we do the numerical application. What do we get? V2 squared over 2 will be equal to H1, that is 1326.4 minus 1211.8. And these are units of what? BTULB, so be careful now, plus, what is V1? Is 100 feet per second square divided by 2. Okay, so obviously we have a problem of units, no? Okay, so how to do this? If you want, we need to have BTUs. So the first thing will be to put BTUs over here, okay? So if we remember from that page conversion, we have that 1 BTU is equal to approximately to 778 foot pound force. So now we have the BTU, but we have the pound force instead of the pound weight. So then what do we know? 1 pound force will be equal to 32.2 lb foot second square. No, I do here F equal to ma. No, yeah, where A will be the actuation. So over here you see that on the right hand side, the LBF will cancel with the LBF. The foot here will cancel with the foot. Then this second square over here, we cancel with this one. So you have foot square over here. And we are left over with pounds, sorry, BTUs per pound. So if you do this calculation, you get that V2 square over 2. I do it for you since I have it for once, is equal to 114.8. Next, we do exactly the same thing, but this time over here, instead of having V2, we're gonna have V2S. Okay, so if instead of having V2, here we have V2S, we can rewrite the same expression as this one, but here will be V2S, and here instead of being H2 will be what? H2S, no? Okay, so this time will be going, instead of going from here to here, we'll be going from here to here. All right, so we could just say following the same approach. So following same procedure, we could rewrite that V2S squared over 2 will be equal to what? H1 minus H2S instead of H2 plus V1 squared over 2. So in this equation, we know V1 because we just calculated V1. I mean, V1 is given to us, sorry, it's 100. We know H1 because we just found it from the table to be equal to what? 1,326. Now what do we need to find? H2S, that will be over here, okay? So we need two things in order to find H2S. What are the two things that we know? On H2S, we know the pressure, and what else are we going to know? The entropy, no? Okay, so basically those would be the two things we use. So to find H2S, we need to know two things. That will be the pressure, so P2 equal to 40. And we know S2S will be equal to S1. So maybe we could go back to this table over here, which will be table A4E, and add here the value for S1 for 140. So let's see, 140 here at 600. We had 1,226.4 for the enthalpy. The entropy will be 1.7191. Okay, so basically I just added here this S1 equal to 1.7191, which now I can use over here. 1.7191. So the state, we still know that the state in 2S should be steam, okay, or superheated gas or vapor. So we know we need to go to table A for E, but probably what are we gonna have to do? Interpolate, no? I'd be surprised that we are that lucky to have exactly that value. So we know 40. So we need to go to 40 here now. And what do we have? 1.7191. So that means that we are between this value here and this value here, no? Okay? So we need to interpolate. So let's say, so for S sub A, let's say will be 1.6993. We have that H sub A is equal to what? 1,186.8. For S sub B equal to 1.7312. We have that H sub B will be equal to 1211.8. Okay? So again, we know that we need to interpolate. I mean, by now, I hope that you don't need this figure, but what do we need to find? H. So you put the H on the Y. Here is what we know. We go between A and B. Okay, to H to S, that will be over here. So that should give us what? H to S should be equal to H sub A plus the slope of this curve, that will be H sub B minus H sub A divided by S sub B minus S sub A times this space over here, that will be S to S minus S sub A. And I have here the value for U. This gives you a value for, after you substitute for with these numbers, that gives you a value for H to S equal to 1,202.3. Okay, so now we can go and substitute into this equation to find what would be the ideal, if you want, isotropic velocity. So we substitute into V2S squared divided by 2 should be equal to H1 minus H2S plus V1 squared over 2. So that's going to give us that V2S squared over 2 equal to what? The H1, that was equal to 1,326.4 minus the H2S, which is 1,202.3. Remember, this is BTUs LB, and here would be exactly the same thing, plus feet second squared divided by 2. We need to do the unit transformation, so it will be 1 BTU 778 foot-pound-force, and then we have that 1 pound-force is equal to 32.2 feet per second, and this is going to give us that V2S squared over 2. What should you get? A higher value or smaller value than the one we had before, than the 114.8? Higher, no? Because it will be the ideal case. So if it was no losses, the ideal case should give you a 124.3, and this should be actually feet per second, okay? So finally, the nozzle efficiency is equal to what? So that gives us the, what do we have before? 114.8 divided by 124.3, which gives you 0.924, which basically is approximately, let's say 92.2, I mean, it's approximately 92.4% efficient. Okay, so this will be the answer here. Now I have a doubt to know if we did this part or not. I think we did it, but I'm not 100% sure. Guys, did we look? I mean, I'm going to ask you, but I'm not 100% sure you're going to be able to respond me. Did we look, guys, for the ideal gas equation, which is what, table 820, some of that, I think it is. Yeah. How can I get rid of this stuff? I mean, oops. And it's right where I don't need it. So did we look, you see here for isentropic, this is equal to 0. Did we look at what was the meaning of the P sub R and V sub R? No? No? Okay, so let's do it then, okay? So basically what we're gonna do next is for the ideal gases, you can see that we also have, instead of having the S, we have the S upper knot over here, but at the same time, we have two more variables on the column, which are P sub R and V sub R, okay? So let's see what these three means over here. I think we did this one. I don't know about these two, okay? But let's just redo it anyway. Okay. So let me go to another page. So let's call over here these tables. Since this is only on the tables, isentropic, quantities P sub R and specific volume V sub R. Okay, so recalling from TDS relations, on the derivation we had that the change in entropy was equal to Cp dt minus R log P2 over P1. And I'm pretty sure that we have done it. So from the class notes on page 84, we already saw that this S uppercase sum naught is basically represent this term over here. All right? And that will be from the table 822, the one we're looking at now. Let's see. I guess this is table 822E. So this is the S sub naught over here. All right? So we know what is the meaning. So basically, we already know that this term over here will just be, this is T1, T2. This is S upper naught T2 minus S upper naught T1. So basically we know that the change in entropy is equal to what is S upper naught T2 minus S upper naught T1 minus R log P2 over P1. Okay, so now what do we know? For isentropic process, what do we know? Isentropic means that the change in entropy is zero, no? Okay, so that means now that we can take this equation and equate the left-hand side to zero. So that means we have 0 equal to S upper naught T2 minus R log P2 over P1. Or this will give you that log P2 over P1 will be equal to what? S sub naught T2 minus S upper naught T1 divided by R. Guys, somebody mentioned that, and it's right, on the previous notes, we use the R bar. Okay, so let's use the same notation for these ones, R bar, okay? So in all these ones here, just add the bar on top of the R. Okay. And now basically, I mean, you probably see where we get here. So this will give us what? If we find the ratio P2 over P1 should be equal to the exponential function of S sub naught T2 minus S upper naught T1 divided by R. Okay, so now using the exponential properties, we have P1 over P2. Again, this is not important, the derivation, but this will be equal to E S upper naught T2 divided by R divided by ES open not T1 divided by 1. And this is actually what they call the ratio PR2 over PR1. So basically at the end, what we have is a relation that relates the final pressure, the ratio of the final pressure to the initial pressure to the PR2, PR1. So again, here, remember, this is only valid for what? For ideal gases and isentropic process, no? So let's put it here. Only valid for ideal gas and isentropic. Okay, and you will see how this is used in a problem. Yes, they're all supposed to be R bar. Sorry for that. Again, R bar, R bar. It doesn't change anything. No, not this R here. This is just a subscript, okay? This one, yes, this one should be an R bar, but this one should not be. This is P sub R by referring to this ratio over here. This P lowercase r, okay? And now we need to see what would be the V sub r, okay? But that's very easy. So this should be page 101. Okay, so this is very simple now. So using ideal gas relation, PV equal R bar T, what do we have? V will be equal to what? R bar T divided by P. Okay, so basically it means that if we do the ratio, V2 over V1 will be equal to what? R bar T2 divided by P2, and here we have R bar T1 divided by P1. So this will give you T2 over T1 times P1 over P2. Now, from the previous relation, this should be equal to what? T2 over T1 times P1 over P2 should be equivalent to PR sub 1 PR sub 2. Okay, and all this ratio, all this value here and all the lower one here is what is equal to, so it should be I mean, doesn't matter the expression. This should be the V sub R sub 2 divided by the V sub R sub 1. So basically what it means is that the V sub R is equal to what? Is equal to PR over TR, no? I mean, it doesn't matter. What matters at the end is that V2 over V1 will be equal to VR2 VR1. Oops, so let's do it here, quick just summary here. Okay, so let me put in big because I want to make sure that it's isentropic, which means what? Delta is equal to 0. Ideal gas relations. So it needs to be isentropic and an ideal gas. Then you can use the relation P2 over P1 equal to PR2 over PR1. Or you can use the relation specific volumes VR2 over VR1. V2 over V1 equal to VR2 over VR1. Okay, so any question? So just like I mentioned, the first example we're going to look at is that what is the simplest modeling that you can do for the engine of an aircraft? And I'm not talking about a piston engine, okay, like a propeller. I'm talking about like a good commercial aircraft engine. All right, so the modeling of aircraft engines. So if you want, I'm going to put it right now. So the ideal things that can model the aircraft engine is what is called the Brayton cycle. So I hope to be able to cover Brayton cycle for sure. And then there's another type of cycle for steam machines for vapors, which is the Rankine cycle. Okay, but let's just first look at this one since most of you are aerospace. So what is the general shape of an engine? We already talked about it. The first part would be the compressor, which function is to compress the incoming air, no? Okay, so if you want, you have air coming here with a certain velocity. All right. So the air comes, at a certain pressure. This is the compressor. Which is going to tell you here that the pressure here is much higher than the atmospheric pressure, no? Yep. So you increase the pressure. Now, in here, you have a control volume. What do you do in that control volume? Let's say you're going to inject into the compressor, into here, fuel. So if you put fuel inside and you ignite it, what are you increasing? The internal energy, no? Yeah? And now, so basically, and what is internal energy plus P times V? This will be a constant volume. What is U plus PDV? Enthalpy. Okay, remember we had enthalpy. So that's why here you're gonna get a lot of enthalpy. Here, you get a very high enthalpy. And now, what is the name of this last component over here? The turbine. So what is the turbine going to do? It's going to transform all that extra energy that you have, transform all the enthalpy into kinetic energy, where V2 should be much higher than V1. Okay? And what else? What is the other thing that the turbine is going to do? So the turbine creates power, and it's also going to create power to drive the compressor. Sorry. Okay, so that's basically the main function of the engine of an aircraft. So, what is the Brayton cycle? So the Brayton cycle basically will be, so first, this is a power cycle, no? All right. So if it is a power cycle, what will be the general form of this figure here? It should be hot, fuel hot. This should be here your engine that operates between a hot and a cold temperature reservoir. And this is supposed to generate power, okay? Remember, I told you that this is the most important figure, because what does that figure tell you is that every single engine operates between two temperature reservoirs. And that is why you cannot have a 100% efficiency. First law of thermodynamics will be just like eliminating this one, no? Okay, but you know it's always this one, okay? So really the modeling of the Brayton cycles, what it says is that you have on one side, you have a compressor. That is driven by a turbine. And obviously over here, between these two, what do you need? You need to have the two temperature reservoirs. Okay, so this should be, for example, here, Q in, and this will be a heat exchanger. And here you have a Q cold, so Q out, and this will be another heat exchanger. So you see here, this will be the power, the engine will be these two over here combined, And then you have the hot reservoir over here and the cold reservoir down here, okay? Okay, and let's add one more thing on the figure. We know that the turbine will generate power, but that the compressor requires power. And let's put some numbers over here. Let's say this would be 1, 2, 3, and 4. Okay, so the whole thing is to find what is the efficiency of all this cycle over here. So let's first look at the turbine. I don't know how far we're going to be able to get today, but let's first look at the turbine. So we do a quick sketch of the turbine, a quick little figure of the turbine. This will be our control volume. We know this is between 1 and 2. Sorry, 3 and 4. I don't know what I'm doing. So this is 4, and this is 3. And that this provides power. So it's always the same procedure. I redo the figure. Now, if we apply the first principle of thermodynamics to this one, what do we have? Q dot minus power generated by the turbine plus M dot H. So what goes in over here will be H3 goes in. What comes out will be MH4. So again, this we should know how to do it. There is no heat gain or loss of the turbine. So let's say this is 0. So basically, you know the amount of power that is generated by the turbine should be equal to M. So will be a move to a1, H3 minus H4. Or let's just write this as power per unit mass will be equal to H3 minus H4, okay? Okay, we're going to do something similar for the compressor. Okay, maybe before we move to the next page, let me add something here to give you direction. What is the efficiency for any power cycle? Is whatever you get out divided by whatever you put in, no? So what are you getting out? The power, what you put it in? Q hot, no? And we say the amount of power you put in is equal to what? So the amount of power you get here will be what? The amount of power, the difference between what is created by the turbine and the compressor, no? Will be power of turbine minus compressor divided by Q hot, no? Okay, for this case. So we found this one for the turbine. We need to find now the one for the compressor. And then we need to find the Q in over here, which will be our Q hot. Let's see if we have time to do that. So page 104. Now we're going to look at the compressor. So if I do a figure of the compressor, this will be our control volume. This one requires power. And this one is the one that's operating between 1 and 2. And if we apply the first principle of thermodynamics to this one, we have Q minus work compressor plus M dot H1 equal to M dot H2. As before, there is no heat gain or loss, so Q dot equal to 0. So this is going to give us that the power required by the compressor per unit mass will be equal to H1 minus H2. Okay. Okay, so now from this expression we need the Q hot. What is the Q hot? Q hot will be the Q in, no? On top. So again, it's the same procedure. So for heat exchanger, you do a figure of the top heat exchanger between what? 2 and 3. This is your control volume. And what do we know on this one? We have the Q in, which will be our Q hot. So again, we write down our first principle of thermodynamics. You see, it's over and over the same procedure, no? Q dot in minus power plus M dot H2 equal to M dot H3. This time, what is 0? The heat exchanger does not require power, no? So this time, this is 0. So we're going to have that Q in per unit mass, if you want, M dot will be equal to what? H3 minus H2. So now, remember that we know this is a power cycle, and we see the efficiency will be the difference between the power generated, so will be the power that is created minus the power used by the compressor divided by the amount of heat we put in. So the efficiency will be equal to the power generated by the turbine minus the power generated by the compressor, used by the compressor, divided by the Q in. So this is going to give us what? The work of created by the turbine per unit mass is H3 minus H4 minus the one of the turbine minus the one of the compressor is H1 minus H2, because we can cancel out the M's, okay? And the Q in will be H3 minus H2. So if you want, finally, the efficiency is H3 minus H4 minus H1 minus H2. H3 minus H2. So this will be the Brayton cycle efficiency. Oops, sorry for that. Okay, so let me just put over here, and which is true. Most of the time, a lot of the power that is generated by the turbine is sent to the compressor because it requires a lot of power to run the compressor, okay? So what we want to know is that what is the amount of power that is sent back to the compressor? And for that, they use some special terminology. So let's say typically, a great amount of power generated by the turbine is used to run the compressor. And it is measured by something that they call, and is measured by the back work ratio. So the back work ratio that they call BWR basically is just the ratio of the work of the compressor divided by the one of the turbine. So basically is the percentage of the total power. The percentage of the power used by the compressor divided by the power generated by the turbine. So we said that the power generated by the compressor was equal to what? H1 minus H2 divided by H3 minus H4. And be careful because this value can only be positive. So I think this term here can be negative. H1 over H2 will be negative. So let's just say it will be the absolute value, okay? Okay, and one last thing before we finish today's lecture. So page 105. So what is the typical form of the Brayton cycles? Oops, forgot the L here. Brayton cycle. If you do a PV diagram, or if we do, let's say, a TS diagram, so a Brayton cycle will operate between two different pressures. Okay, so we have, and then so we'll have something like this. Generally, it doesn't matter how you put the numbers, but this will be. So you start from a lower pressure on the compressor. So this will be what happens on the compressor, no? You go to a low pressure, to a high pressure. Then what happened on the when you put on the control volume? Is control pressure now the control volume over here? I mean, this part is control volume, and then on the turbine you go back over here. And if we do that on the temperatures, oops, that's the way it would be. 1, 2, 3, and 4. So 1, 2, 3, 4, and this will show you that process 1, 2 will be isentropic, and process 3, 4 will be isentropic as well. Okay, so once you go to your proportion class, obviously you're going to look into a lot more detail into this, no? But this is basically the simplest model you have in order to modelize the engine of an aircraft, or what is called the Brayton cycle.